Hello everybody, I hope that this live stream's working. I have reinstalled my computer a while ago, so it may or may not be working. So if somebody could let me know in the chat feed, if there is a chat feed, that this is working. So, get anything on the channel. Try to look for myself on the YouTube.
Okay.
Okay, we are online?
Yeah.
Okay, sweet. Alright, so I got some email questions. I got about 4. Oh, come on. I don't need a keyboard assistant. Just go away. I got some email questions, so I got about 4 of them. So the first one comes from Brandon. He asks, could we go over the gear ratio and the calculation? So hopefully, that one, yeah. Screen over there, you'll find a little website that I found on gear ratios. They do a better job than I did. So it seems that gear ratio is the rotations of the driver or driving gear is to the rotations of the driven gear. So it's a way of representing how quickly these two gears spin. So if you are spinning a small wheel next to a large wheel, then the gear ratio sort of represents for how many times this one spins makes the other one spin. And the calculation is basically you can use the teeth, the number of teeth on the gear, to do the calculation. You can also do a division with this, and that's also, it gives you an indication of how many times these two gears are spinning. So if I flip over to the iPad, so we got gear ratio. Okay, hopefully that's still big enough on screen. So gear ratio is okay, so that's the basic definition there, where you normally have gear ratio is equal to the driving, but the website used the word driver, so drive gear is to the driven, the one that you are spinning afterwards. So if I have a small gear next to a big gear, and I'm going to color these. So driving is my effort gear that I'm trying to do myself. So if this is my driving gear, and let's say it has a tooth count on this one, let's say it has 12 teeth, so I have 12 in my ratio, is to, and then for my driven gear, which I'm going to highlight in red, I'm trying to keep the colors consistent, so I often use red for load. Let's say it's a nice even number as well. Let's say this one here has a tooth count of, I don't know, let's go with 24 teeth. Then I got a ratio of 12 to 24, but I think we've been learning this term in maths class that you can actually simplify ratios, because ratios are similar to fractions in a way, and you know that you can simplify fractions. So let's do that. So I can divide 12 by 12, which gives me 1. I can divide 24 by 12, and I get an answer of 2. So essentially the ratio for this gear combination is 1 is to 2. That means for every one time you spin the driving gear or the drive gear, every time you spin that once, you will spin the driven gear or the load, you'll spin that twice. I think that's the way it works. Driving versus driven. To check the console, is that it? It is rotations of the driver gear is to rotations of the driven gear. Gear ratio is representing, just double checking, because sometimes I'll have these things back to front, which is a bit embarrassing. Every rotation 3 to 1. The order of the two numbers of a ratio is very important. In this case, the ratio of a 15th tooth gear. And anyway, I'll provide a link to this website that I'm looking at here. You can go to that one. It's really good. It's got pictures, it's got little activities. It's much better than what I could do. So I was actually gonna redo these things on Monday, Tuesday class, because I still think that I should look up a bit more on this one. Okay, I'm going to go to the next person's question from the emails. Jacob asks, this is a math one. So Jacob asks, can you answer these questions using the distributive law and expand the following? So he's asking about the distributive law. Oops, that's not how you spell distributive. Distributive law. I hope this pen is big enough for people to read. Distributive law is basically that thing where we had terminology when we were studying it in class, but essentially that's what it is. He has two examples he would like me to solve. We can do these pretty quickly for Jacob. This is pretty quick. So x outside of 100 plus 3x. So if I do my first multiplication, so x times into the brackets, it will be x times 100, so I'll get 100x as my first bit of the solution. And then I go to the next, which I'll use in blue. I'm going to attack, so x times 3x. So I've effectively got x times by 3x. So I've got two x's and they're multiplied together. So that's going to give me an x squared. So this term actually becomes 3x squared. Color one, let me switch. Okay, so that answers the first little demo one for him. The second example he wanted me to solve was negative 17 outside of, 17y. So there's a pronumeral there. Negative 17y outside of 2y, take away 10x. Okay, so what makes this question here more confusing or more tricky is the fact that they're using negative signs. So you have to keep in mind the rules that we have with a negative number times a negative number, and they'll cancel out and become positive. Or if you have a mixture where you have a negative number times by a positive number, and therefore negative wins overall. So you have to sort of remember those mathematical rules. So here my first attack is going to be 17y multiplied against 2y. In fact, it's actually, if there's so for your view, I think, yeah, if there's a negative sign on this side of the number, then that is basically attached to that number there. So I've got a negative number times by a positive number. So my first term is going to be a negative result, because negative times a positive gives me negative every time. I have to do 17y times 2y. 17 times 2 gives me 34, I believe. And then y times itself will be a y squared. So that's my first term. Now I start looking at my second term. So I'm doing this number multiplied against this number. Notice that we got negative. So I got negative 17y multiplied against by negative 10x. So these two negative numbers are going to cancel out. They're going to become a positive result. So my answer is going to be a plus something term. And now I just do the 17 times the x. So I think that is, 17 times 10, which gives me 170. And now you've got the y times x. Now these aren't the same letter, so they're just going to be listed next to each other to represent that they're still multiplied. And you should try and put the pronumerals in alphabetical order. So y comes before xy. Yeah, x comes first in the alphabet. So xy should be the final result. I hope that helps, Jacob. Moving on to my third of the 4 emailed questions. Sophia asks, she asks, can you show how to solve this question? Question is 15.42 divided by 10 to the power of 4. Okay, so we've done these ones before, and put something else that's identical in value, but it's just written in a new form. So I know that I can rewrite 10 to the power of 4. So 10 to the power of 4 is 10 times 10 times 10 times 10. So it's still the same question. I'm just swapping it out for something else that will help me later down the road. And if I just keep following where this leads me, 10 times 10 is 100, times 10 again, 1,000, 10 times 10 once more, I get 10,000. So now we end up with a question that I think Sophia would recognize, where you're dividing it by 10,000. So we're just going to move that decimal place. I guess you have to ask yourself, is my result going to be a smaller number or a larger number? If I'm dividing by 10,000, it's definitely going to get a smaller result. So that helps me make sure that I'm moving the decimal place, the correct number of spaces. So I've been teaching my students that for every 0 you have, and when you multiply by 10 or 100 or 1,000, or if you divide by 10, 100 or 1,000, you count how many zeros there are. In that case, 10,000 has 4 zeros written in it. Therefore, I need to push my decimal place in my result. I need to push it 4 times. So I'm going to push it this direction, because when I do so, my answer is going to get smaller and smaller, which makes sense. I'm taking a number and dividing it by a bajillion, so I should get like a really small result. So I move that twice, 3 times, 4 times, so my decimal point should end up being there. I'm going to put some placeholder zeros. So my result should be 0.001540. Hope that helps, Sophia. Isabella asks, could we she missed out on the lesson for mechanical advantage. Mechanical advantage is a representation of how much a machine, so it could be a lever, a pulley, or a gear, I think even, where you calculate how much the machine multiplies your effort to sort of show how many. Okay, so that means that if I can lift number, the denominator being a very small number, then I've got a machine that's going to make the job easier. It's multiplying it. Okay, so if I've got a lever and I've got I don't know, got a really fat cat on this side, and let's say this cat here has a weight force of, let's say, 3,000 newtons, or 300 newtons. 3,000 might be a bit much. And then let's say I have got Physics Cat on the other side. Here's Physics Cat Potato. He's trying to... That doesn't really look much like a cat. So he's trying to push down on his side of the lever to lift up the fat one. And let's say he's using just 30 newtons of force to do so. Then we can actually calculate how much this machine, the machine being this thing here, the lever, how much is that giving Physics Cat extra strength. So it's load divided by effort. My load was 300 newtons, and the effort that the Physics Cat is trying to lift the other one with, he's only using 30 newtons of force. And the wonderful thing about fraction is that not only do you simplify by finding common factors, you can also simplify by dividing common units. So n divided by n cancels out to just 1. 0 divided by 0. So I just get 30 over 3. I should get a mechanical advantage of 10, I believe. Meaning that this particular lever, in this particular example, that lever is multiplying Physics Cat's strength 10 times. Alright, so that's for Isabella. Now I can get to the chat feed. So my wife is currently managing that, so I can't see your chat questions directly, but I do have a bit of a summary list down here. Otherwise, I would lose track of all the questions. So the first one is it Austin, my son? No, say. Normal force works without gravity, right? Does normal force apply without gravity? Well, normal force is the repulsion between the atoms of the object you're touching and the atoms in you. So if I have I guess two answers. You never escape gravity. There is always gravity. It's just more or less gravity. So if you're far away from the Earth, like really far away from the Earth, then you would feel the Earth's gravity less, but it doesn't mean there's no gravity at all. So that's one part of the question. The other part of the question is that if I have a ball, let's say it's a football, I've thrown this and it's now hit, I don't know, a alien spaceship. Okay, a flying saucer. So it's hit that object right here. Well, you might say that the gravity of the football and the gravity of the alien spaceship is pretty small, so there's very little mass, therefore little gravity to pull them together. So we can almost imagine that the gravity in this situation here, in the middle of space, has no effect. But when you slam those two objects into one another, wouldn't the atoms in this side of the ball also repel the atoms in the spaceship? And if so, you would have normal force. So you would have a repelling force. So that's my normal force. I'm using Fn, n for normal. And you would also have your applied force, or your effort force, from the ball slamming into the spaceship. So you'd have F, I don't know, push. Okay, so you would still technically have a normal force even without gravity present. It just requires two objects to make contact. So if they contact really lightly, then you got very little normal force sort of repelling away. If you had them hitting really hard, then you'll get a lot more normal force. Moving to the next question, Brooke asks, can you touch base on the word problems in the maths practice test? Word problems in the maths practice test. Brooke, you have to be more specific, because I'm sure there's a ton of those. I don't think I'll be able to get through all of them in the space of half an hour. It's already been 18 minutes, so if Brooke can rephrase her question to a particular one, otherwise I'll spend an hour or so talking about them, so I don't think that'll be fair if I do them all at once. I will do your second question though, Brooke, which is, how are magnets made? Is it just by having iron with the magnetic domains lining up? A magnet is made when you pour, so if I've got, here's my molten iron, I'm pouring it out of a bucket. I can pour it into a mold, so here's a trough, and my molten iron can fill in that trough. Let me just shade that in so people can see what I'm talking about. So okay, so I can pour my molten iron into there. Now, while the iron is hot, okay, so before it has a chance to solidify, if we look at the structure of that iron under like an extreme electron microscope, we would find that they have their little, they would start to form little crystal grains, right? I think you have learned this in my class. If you're not a student of mine, you probably have never heard of crystal grains. That's fine. You don't need to know. Just focus on what your teacher has told you. This is just something that I find really cool about chemistry, so I showed it to my students. It still has the same sort of outcome in terms of what's going on. When it's still molten, all the atoms are still, technically in molten state, all the atoms are very separated. They don't have any arrangement. They're all very random. Think of it like a ball pen at McDonald's, but it's like everything's flying around. All right, so lots of wind just chucking up all the balls everywhere. Very random. But as you cool everything down, the wind and all that sort of things making those particles fly about, they start to become less and less, and they start to calm down and come together, and such to the point where the attraction between atoms can start to sort of connect them. And then when they start connecting, they'll make like a cluster, and we call those clusters a crystal grain. And that's what I was describing in my classrooms, where eventually each cluster will keep growing and growing and growing, and there'll be a neighboring cluster also growing and growing and growing, until they basically they're going to create little countries or boundaries between each one of them. And that's what I'm describing in the class notes. Each one of those boundaries is going to have a magnetic domain. Domain meaning where you live. So if I'm saying magnetic domain, basically its own, that area of the metal, it has its own magnetic field, or its own little magnetic pole. But when you have ordinary iron, it just tends to line up randomly. So these magnetic domains, which I'm representing with arrows, they just tend to be in randomized directions when you have just ordinary iron. But if you want to make a permanent magnet, you want to have the whole cooling down process to take place nearby an existing magnet. Because if I have a magnetic pole right here, so here's my north end of my magnet, south end of the magnet, I am going to have the magnetic field lines going like this, coming out of my magnet. Okay, and we know the magnetic field lines go from north to south, so I'm just going to use these arrows. Okay, the more times you see this, the better. That means that if I have my little crystal grains, they're growing inside of my solidifying metal to make a new magnet. That means that each one of those magnetic domains is going to align. They're all going to follow that magnetic field of the magnet nearby. And then when it finally finishes cooling down, they're locked in place, meaning these crystal grains, or these magnetic domains, they can't twist back or go random anymore. They stay this way, and so they stay in alignment, and therefore all of those individual little magnetic fields, they all basically work in the same direction, makes them more powerful. Therefore, this ends up becoming a permanent magnet. Going to the next question, which is for Tanya, I presume for Lauren. Could you touch base on multiplying decimals? Okay, so if I've got 2.301 times by 0.102, so here's multiplying decimals. The trick with multiplying decimals is that you just temporarily forget about the decimal place. So just pretend they don't exist, then do a multiplication as you normally would, and then at the very end, you just stick in the number of decimal places that it should have had. So if I have something that has 3 decimal places, so this one here, 301, that's 3 decimal places that I have technically. Basically, the trick works by taking the decimal place and moving it back. Okay, so I've moved it back 1, 2, 3 times. So I'm just saving that number in my head. I've also done this the similar amount for the other number here, so that makes it 4, 5, 6 times. So once I've put them away and I solve the maths, when I get to a final number, I need to stick my decimal place and bring it back up 6 spaces. So let's do this one here, and everyone can laugh at my inability to do multiplication in my head live on screen very well. Okay, so 1 times 2. 2 times 1 is 2. 2 times 0 is 0. 2 times 3 is 6. 2 times 2 is 4. I'm starting a new line of maths. I need to put down a 0 first, because I want to do 0 times, 0 times everything will just be 0, 0, 0, 0. Now I'm going to my next column here. I'm going to put down 2 zeros because I want to do 100 times everything. Yeah, so that's where those 2 zeros are coming from. 1 times everything. Add them all together, so I get 2, 0, 7, 4, 3, 2. So there's my final result. Now, like I said before, you're just going to stick back the decimal places that you've temporarily removed. Now, don't stick them in here. I don't like that, because if you stick in your decimal place, if you put it in, let's say there, then what you've got here and what you've got here are not, they're not equal. Okay, so you've made a, I like to call it like a grammatical error, like poor sentences. So mathematically, that's not true. Okay, you're not saying that the top part and the bottom part is equal to each other. So when you do replace the decimal place, put it somewhere else. So I would go maybe therefore, those 3 dots symbol, or you can just write the word therefore if you like. I'm going to copy down the number and replace my decimals. So I'm going to push it back. So currently the decimal is here. I'm going to push it up. How many spaces am I going to push it back up? I'm going to push it back, let's see, 1, 2, 3, 4, 5, 6 times. So I'm going to push it back the opposite direction 6 times. Here we go, 1, 2, 3, 4, 5, 6. So it's now sitting here, and I have to put a 0 there, and I'm done. So the actual answer is 0.23470. Hope that helps, Tanya. Moving on to Brooke's question.
And dividing decimals?
Oh, did I miss that?
No, she just chucked it in the chat now, but we may as well while you're talking.
Okay, so for dividing decimals, well, this is continuing on for Tanya. Let's say I've got 1.42 divided by 0.12. When you do dividing decimals, we have to pull out a different trick. Okay, so the trick that really works well for this is the fact that division is identical to fraction form. So I can say the top line is exactly the same thing as 1.42 all over 0.12. Now that I have it in fraction form, I know a few tricks to try and make this something I can solve. Now, fractions don't have decimals within the top or the bottom, so it looks wrong at the moment, but I can fix that. I can actually scale the entire thing by multiplying it by some power of 10s. I could multiply it by 10, I could multiply it by 100, I could multiply it by 1,000, or anything like that. I just want to multiply enough, just enough, for the bottom number, okay? So don't have to worry about getting rid of the decimal places on the top. That's not important. What's most important is you focus on pushing the decimal place such that you can bring it back to make the bottom a whole number. So I need to move that back twice, and I gave you that trick that if you have, like, you're timesing by 10 or timesing by 100, the number of zeros you have in here gives you a clue as to how many decimal places you can shift along. So I'm going to times by 100, same thing top and bottom. So I should get 142 all divided by 12. And then to proceed from there, we can chuck that through short division. And now I'm regretting my decision to use 12 times tables. So it goes in there once with 2 remainder, 22. It's in there, only it's in there once, doesn't it? I need to pull out a decimal place. So 12, 8, 10, 10 remaining, so now 100. Okay, it's oops, I don't put a 0 there. Anyway, you're going to keep going there. I'm not that confident with doing 12 times tables really quickly on my head, but essentially this would be your answer once you've done the division process. That number would go in here, so 11 points, blah, 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 blah. Okay, going on to Brooke, who's got another question. Can you give a definition for static electricity? Static electricity is when you have an object has an imbalance of positive and negative charges as a result of rubbing together. So if I have my blazer, which usually has polyester on the inside of the lining, and I might be wearing a woolen scarf, and if those two materials rub against one another, there will be a transfer of electrons across from one material might not be that strong at holding on to its electrons, and the other material might be really hungry for extra electrons. So when you rub them together, you give them a chance for the electrons to make it across the gap. Therefore, one object, so if I've got a balloon, for example, and I've got okay, this is my hair. So if I've rubbed the two together, normally everything has an even balance of positive and negative charges. Okay, so 1, 2, 3. So the balloon is balanced, neutral. The head, 1, 2, 3. So there's an equal amount of charges. However, the balloon rubbing against hair, the balloon is really hungry for electrons. So when you've rubbed them together, the electrons jump across to the balloon, and so now all those 3 charges are end up in the balloon. So now if we count up the charges, we've got 6 negatives and only 3 positives. So this thing here becomes negative overall. And your head, or your hair particularly, becomes positive overall. Okay, you've now created a static electric charge. We use the word static because static means or stationary, all right? It means that they're not moving. So once you've done the rubbing process and you've moved them apart, that charge can't go anywhere. Not unless you bring them together, or not unless you are able to bring the balloon to something else where it can then pass its extra electrons away gradually over time. So that's what I would go with. If that definition is messy, then one alternative you could do is you could Google definition static electricity for science for kids, and you'll see some probably some really nicely put together definitions that other teachers out there have done. But for me, it's an imbalance of charge on 2 different objects after they've been rubbed together. Okay. Brooke had more questions.
She has many questions.
Goodness. Can I postpone Brooke's questions because I've already done several of hers. So if we can cut and paste her lightning question to the end of the list.
Sure.
I'll jump to Alex. Alex asks, what are the 3 types of levers? First class, second class, and third class lever. Well, if you want me to go into it. Okay, first class lever. First has fulcrum in the middle. First starts with letter F, fulcrum starts with letter F. You put the fulcrum in the middle, so there's a balance on the seesaw. Once you got that, you can easily just figure out what goes in the end. So obviously I'll have a load on one side, and I must have, effort on the other side. Okay, so. And if these two, if the green and the red, if they're back to front, then it just means I've turned the entire lever back to front, and it's still the same type of lever. Second class lever. Second is load in the middle. I like to call it second round. You need to reload your gun. I don't know. Some way of remembering what goes. First class fulcrum in the middle. Second class reload. So load's in the middle. So I'm going to put load right here. I can put a nice big cat here. He's sitting on the middle of the bench. Now, what you're just going to do is where's the fulcrum going? Well, the fulcrum has to be somewhere, so I'm going to put the fulcrum on this side, just by choice. And the effort has to go somewhere. Well, the effort has to go somewhere on the other end. So effort would go on that side. And this is basically a wheelbarrow, isn't it? So if I just replace this triangle for a wheel, and the cat is now sitting in a bucket, I've basically got a wheelbarrow. So second class, loads in the middle. Third class, I reckon third class people have to work harder than everyone else, so third class effort, you have to put in the effort in the middle. So effort is here. Then you have to decide, okay, where's my fulcrum go? Well, it could go left or right, doesn't matter. So I'm going to put my fulcrum here just by choice. And then my load has to go somewhere, so my load's going to be here. Okay, so that load could be again like that cat. Okay, and the effort is right in the middle, so this is basically our catapult, isn't it? We can slingshot the cat really, really fast. So, next question. Amy asks, how do you do the working on question 10 on the practice maths exam? Okay, give me a second. I'm going to go try and find out which question that was. Practice exam, question 10. Let me just double check. Did they specify whether that was... Can you get Amy to specify if it is part A or part B? Part B is the one that's usually the harder, so I'm going to assume she's asking for the harder part of the paper, which is part B. Question 10. Is this the one about the baby mouse doubling its weight? Let's see. Is this the question that you're referring to? I'll resize my window there a bit.
Yes.
It is? Okay. Fingers crossed I can solve this live, because I haven't actually looked at this question before. After 1 week, the weight of a baby mouse is double its weight at birth. Okay, so that means this weight continues to double each week. So it looks like...
Is that 10B?
10, oh, she's asking about 10B?
Yeah, sorry, there's a delay from what you're talking to what I'm reading, so...
10 part
10B.
B? Yep. Or, because there's like 10A, 10B, 10C, 10D.
It says 10B in chat.
10B. Write an expression using powers in deck notation for how much bigger the baby is after 5 weeks. Oh, okay. I can do that. That was an easy one. So question 10B of part B. Okay, it says write an expression using powers for how much bigger the baby is after 5 weeks. Okay, so it doesn't mention anywhere in the question how heavy the big baby was to begin with. So I'm just going to use an algebra letter. So maybe W for the word weight. So, okay, I'm just going to say W is weight of, maybe original weight. Let's go with that. Original weight of baby mouse. Okay, so that's just that's the letter I've chosen. You could use the letter X or, I don't know, whatever you feel like. I'm using the letter W. So it looks like after 1 week, so I'm just going to try and build it out by thinking out loud. I already sort of have some ideas what I might do. After 1 week, it's just going to be 1 times W, wouldn't it? After 2 weeks, it's going to be doubled, so twice the baby's weight. After 3 weeks, it's going to be double again, so 2 times the previous, so 2 times W. Okay, 4 weeks is going to be double that again. So it looks like, looking at the pattern here, let me just highlight these for you. Okay. It looks like the rule is going to be 2 to the power of time, so how many weeks it's going to be, times w. If I was going to make a general rule that could calculate the baby at any point, so you could calculate it, 3 years in the future if it keeps growing at this pace, I could use that little rule there. Power notation, because if I come back in here, 2 times 2w is going to be 2 squared, isn't it? Alright, these two are the same thing, aren't they? And then for this one here, it's going to be 2 times 2 times 2. That's going to be 2 to the power of 3w, isn't it? They're exactly the same thing. So after 5 weeks, I'm noticing this number and this number, it seems to be like it's like one less. So it looks like my result's probably going to be, so for 5 weeks, it's going to be 2 to the power of 4 times w, I think. Let me just check if Mrs. Appleton's thing matches up with what she put 10 to the power of 5. How many times? Maybe I didn't read the question in its entirety. Let me just check that. After 1 week, the baby's mouth is double. After 2 weeks. Oh, I see. I've made a mistake here. Sorry, folks. I didn't read the first statement there. I assume that we're starting from like 0. I need to rejig this, okay? So let's say 0 weeks, 1 week, 2 weeks, 3 weeks. Okay, in that case, these numbers match. So the answer should be 2 to the power of 5 times bigger. Because they're asking how many times bigger, not what is the weight of the baby. So if I wanted the weight of the baby, I would put the weight next to it. But the question's not asking about the baby's actual weight, they're just asking how many times bigger it is than the first week. So I get a result of that. Sorry it took I took a pathway around it, but I think we're all human, but also it helps to rethink your answer. So when I put down when I put down 2 to the power of 4, when I did this originally, part of the process that I had just now is that I was looking, I was like, like I didn't feel like it was right, so I went and searched out the result. So obviously when you're in a test, you can't go look up the answer during the exam, but you can go back to the question and sort of investigate and see, like, did I interpret this question correctly the first time? So that little bit in my I don't know, in your soul, I call it my soul, my mathematical soul, it didn't feel right to have 2 to the power of 4w. So I went back, is that right? And then I went searching out the answer, and I found out, oh, it's a different answer. Then it led me realize, oh, I've read the thing, I've interpreted the thing poorly, so I had to go back and fix it. Okay, so I hope that solve wasn't a complete waste of everyone's time. Alright, going back to Brooke. Can you talk about the force arrows and how to know the length of the arrow, and on the test if we have to write which force each arrow is showing? Okay, so if I've got, I think I had a picture the other day. The cat was like this. It was like a soccer ball, and the cat was off the ground. Okay, so at least the cat's kicking this giant ball. You don't have to know the exact length of the arrow. Okay, these arrows are just there to, the length of the arrow is there to represent relative to each other, how much bigger or smaller they are compared to each other. So the weight of the cat, I'm using an arrow straight down, so I'm just going to use weight. Okay, and the weight of the ball, just think about it, is the ball have as much weight force as the cat? Of course not. So for the ball, I would use a smaller arrow, just as a way of showing that I know the cat has more weight force than the ball does. Okay? Then I start thinking about other arrows going on. So obviously the cat is pushing that ball, so I'm going to need an arrow representing it's pushing into the ball. But I got to think about it. Okay, relative to how much force the cat exerts on the ground, is the cat kicking that ball with more force than the cat would be if it stood on the ground? I think the cat's kicking it pretty hard. So I'm going to choose to show this push as a stronger arrow compared to this arrow. Okay, how long I choose is, that's a matter of choice, but what matters is that I'm trying to show that the kick, the force of the push, is going to be stronger. Okay, and therefore I'm going to have my normal force going back the other way. Okay, so I hope that helps, Brooke, for the arrows. And you do have to name them, so see these words here, that's the sort of thing I'm looking for on the test, if there was a question like that on the test. Brooke also asked, can you put in words how friction works and how lubricant reduces the amount of friction? Okay, friction works by the roughness of two surfaces that are in contact trying to slide past one another. The bumps in their textures, okay, so represented by my fingers, the roughness of the two surfaces, so this is my first surface and this is my bottom surface, okay, and imagine lots of little bumps and valleys, okay. When you push, when they're touching and they're trying to slide past one another, the bumps and valleys are going to get caught on one another. You could describe it as that they are interlocked, if you like, slightly. They're not fully interlocked. They're just going to be slightly catching and resting upon some of the bumps and valleys. Okay, and they're going to resist the direction of sliding because they're going to catch. Lubricant reduces the amount of friction by when you fill the gap between two surfaces. Let's say, I don't know, two gears coming together, for example. Two gears trying to slide past another, you might use a lubricant. Okay, when you apply a lubricant, the lubricant has to go somewhere. So it's going to fill in all the nooks and crannies. But not only that, it's going to fill the nooks and crannies in the other material. And they also make the two surfaces further apart. So now if you look at it, the lubricant is providing a bit of an extra space or a bit of a barrier or a bit of separation between the two surfaces. And now the nooks and crannies can't catch. Therefore, they can slide so much easier, okay? I'm not saying there won't be any catches along the way, I'm just saying there's going to be a lot less, therefore much less friction. Ruby asks, can you explain the gathering of like terms in algebra? Okay. Like terms. Okay, we're about 15 minutes over time, but I don't know if my wife is able to keep going.
Yeah, of course.
Okay.
You have lots of questions.
Oh, shoot. Okay.
So,
Okay. We might go for the full hour and then call it quits and sort of adjourn for tomorrow. But like terms is you're trying to gather terms. A term is going to be something that, 45a over 3 plus 2x, okay? Terms are separated by these, okay? A plus or a minus sign, okay? Or an equal sign. So if I have, y equals the entire thing, then this itself will be its own term as well. All right. So terms are only alike if they have exactly the same letter combination. Letters meaning pronumerals. Okay. So for example, 2a plus 3b plus b. Now, 2a is a completely different person to 3b and b. Okay, see this one here has the same letter b, and you might think, oh, it's not exactly the same. Well, there is actually a 1 in here, but we just generally don't write number 1s in front of everything. It just wastes a lot of time, so we just don't write the number 1 all of the time. So 3b and b, I can add those two numbers together by this symbol. So I'll get an answer of 4b, but 2a has nobody like him, and so he's all by himself and gets left alone. I think perhaps that what's coming from behind Ruby's question is that there was a question on the test which said something on the order of 9a take away 2a squared plus 8a squared. Okay, so again, the rule is they have to have, for the terms to be alike, They have to have exactly the same letter combination, exactly the same letters. I thought about this the other day, how to prove that this is not the same thing. So these two are similar, but this is different, okay? I found a way of doing that. And the way you can show that it's completely different is if you actually break it open, okay? A squared means A times A, doesn't it? So it's basically AA. Okay? I think now you can agree that this doesn't look like the other ones. Okay? It doesn't have the double A on the back end of it. So it's completely different. So therefore we get a result of, I think, negative 2A plus I should get 6A squared 9A. I think I should get that as a result. But again, I'm just going off the memory of what the question looked like. I may have sort of brought it out of my brain a little bit differently. But that's a way of looking at it. Next question. Saxon asks, in the notes you use gravity for the downward force arrow in the example, then weight on another example. Can either be used, or when should one be used over the other? Yeah, excellent question, Saxon. So when we discovered, when we started off with forces, I just used a downwards arrow on an object. So let's say I've got a okay, got an old wise cat. I used a downwards arrow, and I originally called it gravity when we're doing force arrows. But later on we found out that, and gravity is the attraction between any two objects with mass. So you and the Earth, there's going to be an attraction force between your two masses, okay? And I call that gravity. And that is acting in the same direction, so I use downward arrows for that. Later on we started looking at weight as a force as well. Using the formula, F weight is mass times the acceleration due to gravity, mg. So if you have a mass of 30 kilos, I should probably move everything across here. So if you have a mass of 30 kilos, and you're multiplying it by the acceleration due to gravity on Earth, that number is 9.81. It's a magical number, kind of like pi is a magical number of 3.14. G has a magical number of 9.81 for the Earth. It'll be a different value on a different planet. So if I multiply those two together using an earlier math trick, that's basically going to be 981 times by 3. So I'll get 3, 24, 27, 29. So I'm going to get an answer of 2943. Put my decimal place back. Okay, I'll get that many newtons. Okay, so when we started talking about weight force, we learned that it's probably better to describe the downwards arrow as weight. Okay, so because I've used those two terms pretty much interchangeably, I would expect it'd be completely fine to swap those two out for one another. So don't worry about that, Saxon. Both is fine, and I will be marking as such because of the way that I've taught you guys. Next one, Alex asks, what are some examples of contact and non-contact forces? Contact would be like punching you in the head. Non-contact might be the Earth pulling you to the ground after I've chucked you out of an airplane. So here is you, here is me. Okay, and I have hit you with a force, and that's contact because I must have made contact. And here is the platform of the airplane. And you fly outwards, but you're still being pulled down by gravity. Of course, the arrow is not going to be that long for gravity. You're not going to fall down quite as fast as I've just hit you. Okay. Okay, so gravity would be a non-contact force because gravity can pull you, can influence you without touching you. Another example of non-contact would be electromagnetic force, basically magnetic force. The other one could be electrostatic force, which is the attraction between positive and negative charges, and repulsion against negative charges, for example. Other contact forces could be north force, could be a push or a pull or a twist, those sorts of things that have actually made contact. Ryan asks, go over how pulleys work, please. Pulleys is not my specialty, but pulley makes things easier. So here's a pulley that I've attached to the ceiling, and here is a rope that I have slung over the pulley. Okay, and this is me trying really hard to lift up, I don't know, a loaf of bread. Okay. Now I might not be strong enough to lift up the loaf of bread directly, but if I use this type of pulley here, I can actually use my own weight along with my arms to pull on that rope, and that makes the job easier. I've just changed the direction I'm pulling, because if I do it the opposite way around, where I try and lift the bread straight away, so let's okay, if I try and do it this way, and here's the weight of the object, I don't have my own body weight on my side. The only thing I have to rely on is my little strength and my little arms. So a pulley can help reduce the effort required by changing the direction of which you lift. Okay, so lifting straight up is really hard. It's hard on your knees, it's hard on your back. However, when you pull down on a rope, you can just, I don't know, grab on it, wrap it around your hands, and just basically kick your feet off the ground and let your body weight pull down that cable. So that can really make a lot of help. When you use multiple pulleys, you can make the job even easier. So if I have, so I'm going to tie a knot here, wrap my string, oops, change color, it makes more sense. I'll tie a little knot here, wrap my cable, wrap around there, and pull it. And let's say here I've got, I don't know, something really important like somebody's laptop. Okay. Okay, and they're watching, I don't know, one of my YouTube videos. And this is me. I don't know. I don't know what's wrong with my face, but just go with it, okay? This one here, I can pull the load here being the laptop. Okay, if that laptop is pulling down, you can imagine it's also pulling down on these two bits of string that's attached to it. But that string is also under tension, so it's also got tension going the opposite way. So I've almost got like 50% on this string and 50% on this string. And we know that this 50% is going straight to the ceiling. So I don't have to lift that much. But the other 50% I have to pull that way. So that pulley combination, you can reduce your effort required to lift it, because the ceiling, technically in this case here, is doing part of the load. I don't know if it's exactly 50%, but I think it's somewhere in the ballpark where a pulley system will reduce it by a fraction. So you can make the effort required half or a third or a quarter. I would suggest that you go check out some videos or maybe some websites that are much better at pulleys than I am. But I think that's kind of the idea. It changes the direction of which you pull, which makes it easier, or it can sort of offload some of that effort required by anchoring by the actual connection to a ceiling or something like that. Kind of in the same way that I was showing for ramps. If I've got a so if I'm trying to push up a fridge, the reason why a ramp makes the job easier of getting it to the next floor is that part of that weight of that object is actually resting on the ramp itself. That means I have a lot less to overcome, provided I put some wheels underneath of it, of course. But the ground itself is taking up part of that load, whereas if I didn't, so here's the same fridge. Okay. The entire I have to take the entire load on my legs, on my back. It's much harder work. So when you have it resting on a surface, it can take up some of that and offload it to something else that doesn't really cave in like a spine does. Alex asks, can you write the question for each diagram, then upload it to Google Docs? Sorry, Alex, it will take me far too long. I've already given up basically a full hour of my time. I'm not gonna, that's too much, so I'm gonna say no, sorry. Amy then asks, how do you work out question 11 on the practice math exam, working for question 10 and 11? I presume she's asking about the harder ones. It's going to take a while. Look, it's at the pretty much at the hour mark, 3 minutes to go. Don't think I can answer the question 11 in time. I can give it a try. I haven't seen the question yet.
Put the rest of the questions first.
Should I save Amy's question for next basic?
Just have a quick look through. There are some that should be easy to answer, some that will take longer. Maybe you pick a few that are easy.
Okay. My wife says I should sort of scan through people's questions and pick ones that I can do quickly. I will save the rest for the next live stream. So again, like if you're not there, I'll answer those ones first on tomorrow's live stream. Ryan asks, last question of maths practice test. That's probably the same thing as Amy. Ryan then asks, do we need to memorize how magnet is made? So Ryan, you don't need to memorize how a magnet is made. It's just fun fact that I show to my kids. Ryan then asks, can you please explain? Let me just hide that. Oop, I just scrolled away, didn't I? So that one there I've done. Can you please explain what air resistance is? Air resistance is the difficultness of an object passing through air. All right. So if I've thrown a tennis ball, is that a tennis ball? Now it's a tennis ball. So if I've thrown it through the air. And you know from when we studied chemistry, we did the separating mixtures. You know that you know how some things are made out of like a fine dust. Okay, so imagine even finer particles. Okay, we call those particles atoms. I think you might have seen them in the physics chapter about protons and electrons and stuff like that. So basically, everything that's made out of matter, everything is made out of materials. They have particles. The air itself also is made of particles, oxygen particles, nitrogen particles, and so on. Okay, so they are, oops, let me just change the color of that. So they are all around, and that ball has to pass through it, okay? The problem is that the faster you go, the more air particles gets bunched up in front of you, which makes it harder for you to sort of get through it all, okay? So you have to push through. So that's going to slow you down. Another aspect that's going to slow you down is there's going to be an empty cavity behind the ball. Okay, because think about it. So the air particles in your way, okay, as a ball's going through, air is going to slam into the front of the ball, which is going to slow it down. Air has to travel around the ball, which is still going to slow down the ball. But then the air can't seem to get around into the back part of the ball fast enough. So we call this a bit of a vacuum. So not only is it hard to get through when you're passing forwards, it's also going to be hard because the area behind you is trying to suck you back. Obviously, it's not very strong compared to how fast you're going, but collectively, things in your face and things sucking you backwards, collectively we call this air resistance. And there's many cool things about air resistance, and it's basically the same thing that's going to happen to when you dive into a pool. Like if you put your hand in the pool and you try and push it really hard through the water, obviously you feel it on the forward part of your hand that the water is resisting you, and also behind you can feel like that, almost like at least I have. It feels like something's kind of drawing your hand backwards as you're trying to pass it through really, really fast. If you do things really slowly, then there's plenty of time for all those particles to go around you, which is why you don't feel much resistance in water when you go really slowly. It's only when you try and slam your hand through the water really fast do you encounter that this resistance becomes really, really important. Same thing through the air. When you're driving your car in the car park and you put your hand out the window, you don't really feel much. But if you're going at 120 kilometers per hour in the outback on an unmarked road and you stick your hand out the window and you don't hit a kangaroo, you're going to get a lot of that wind pressure on your hand and you're going to feel it a lot more. So you have to sort of apply more muscles to keep your hand in place. Okay, any other quick questions I can answer before we quit the live stream today? Quantities and proportions. That will take a while, so I might say that for tomorrow's live stream. What is a ratio? A ratio is representation. So this is for Isaac. A ratio, and this is partly related to the question about quantities and proportions. A ratio is a representation of the size of one thing compared to another. All right. So for think you've seen a really famous picture that looked a little bit like this. Okay, and the guy's got long curly hair. He's in like a bit of a circle. Have you seen that one? I think it was made by Leonardo da Vinci. And one thing he was trying to show is that at a certain one of the ideas is that if you stand like this, apparently the size of that is the exact same size as that, and you would call that a 1:1 ratio. Okay, the size of your arm span is identical to the size of your height. Okay, another thing you could consider is that for the human face, okay, for the size of that, let's say that is the size of that and the size of that. Okay, so from the top of your head to your eyes. Okay, if you look at my goofy face a bit longer than you have to, okay, you'll see the top of my head to my eyes. That's about 50%, like right in the middle, isn't it? So for that size there, the head would be double that size, wouldn't it, in terms of length? So that ratio here is for 1 is to 2. So it's a way of representing the scale of something to something else. With your computer screen, it's your video the video right now probably has this ratio we call aspect ratio. It's how wide it is versus how tall it is. The video you're watching right now has a height of 9 units, and it has a width of 16 units. So we would say that for 16 units this way, 16 is to 9 units the other way. It's a way of representing the size of things. If you look at an old black and white television, or the very, very early televisions that still had a bit of roundness to them, so they looked a little bit like, you've got controls down the side, and it's really thick at the back, and you've got some antennas that stick out the side, so it looks a bit like a bunny rabbit. These ones, they don't look quite as wide, do they? They have a different aspect ratio. Their aspect ratio was 4 units wide, and they were 3 units tall. Okay, it's just a way of representing it. So if the actual measurement here, if you took a ruler and took it to the TV set, okay, if that actual dimension was 10 centimeters, then the width of that TV would be 10 centimeters. Maybe I should pick a different number. 10, 3. I should pick a different number there so I can do it in my head. Let's make this unit here 12. 16? I think so. Let's see, 3 divided by 12. No, 12 divided by 3 is 4. 4 times 4 is 16. Yeah, that would be the right ratio. Yeah, it's a way of trying to figure out, if you look at this new ratio, we have 16 is to 12. And we did the other day about ratios that you could simplify them very much. They could simplify, for example, 4 over 2, you can simplify that by dividing it by a common factor. So divide that by 2 gives you 2, divide that by 2 gives you 1, so you get the same thing as 2 over 1, or 2. Here I can simplify these both by dividing them by 4. So divide 12 by 4, I get 3. Divide 16 by 4, I get 4. So I get the same ratio of these two dimensions. So I hope that helps. Look, we're going to have to close the live stream now. I have been working very hard these past couple of days, so hope this helps. I will be back online tomorrow at 4 p.m. for about half an hour, or if you guys are as intense as you were today, I might continue going a little bit longer depending on how much time my wife can afford to help me out. Thank you, everybody. I will see you tomorrow.